Alright, gather round, fellow rockhounds and dirt dabblers. We're diving deep into the fascinating, sometimes messy, and absolutely essential world of rare earth elements REEs. You know, those 17 metallic marvels on the periodic table including scandium and yttrium, which sometimes feel like the forgotten cousins that are the secret sauce in pretty much every piece of modern tech you touch. We're talking smartphones, electric cars, wind turbines, the lot. Demand for these elements is skyrocketing, especially with the global push towards clean energy, which presents us Earth scientists with both a massive opportunity and some equally massive challenges. Now, despite the name, REEs aren't exactly rare in the Earth's crust. They're just not often found in concentrations high enough to be economically viable for traditional mining. And even when you find a good deposit, separating them from each other is notoriously tricky because they have incredibly similar sizes and chemical properties. Trying to separate them is like trying to sort identical twins based on how they interact with water. The differences are subtle, about 0.02 nanometers in ionic RED in water, if you can believe it. Traditionally, getting REEs out of the ground and into your gadgets involves methods that can be, well, let's just say they wouldn't win any environmentalist awards. We're talking open pit mines, underground operations, and then some serious chemical processing like hydrometallurgy and solvent extraction. These processes are energy intensive and generate significant amounts of waste, including tailings and potentially radioactive co-products like uranium and thorium. Plus, you're often dealing with nasty, corrosive chemicals and gobbling up lots of water. The environmental rap sheet includes water and soil contamination, habitat disruption, and general ecosystem unhappiness. Let's not forget the folks living near these operations. There are potential health impacts too. It makes you appreciate the Earth part of Earth science a little less when you see the scars left behind. Enter the promised revolution, commercial in situ recovery (ISR). This sounds fancy because it is an innovative method combining geological engineering with in-depth chemical processing. The basic idea is less invasive than traditional mining. Instead of digging up vast amounts of earth, you inject specialized leaching solutions directly into the ground to dissolve the REEs where they sit. Then, you pump the re-enriched solution back up to the surface for processing. It's like giving the ground a targeted chemical bath and collecting the dissolved goodies. The claimed benefits are pretty compelling: lower production costs, higher technical recovery rates, reduced water usage, less surface disruption, and targeted extraction that minimizes environmental risks. Proponents see ISR as a way to improve market resilience and ensure a secure, sustainable supply chain, bridging economic needs with environmental responsibility. It sounds great on paper: less digging, less mess, more metal. Maybe one day we'll just send chemical sprites underground with little dissolve potions. However, let's put on our geologist's discerning hat and look at the fine print. While commercial ISR sounds like the future, the reality of existing in situ leaching methods, particularly for adsorption clay deposits, paints a starkly unique picture. The ammonium salt-based in situ leaching, as seen in Myanmar, is documented as being environmentally devastating. It involves injecting ammonium sulfate into the earth, which dissolves REEs as it tracks downslope. The consequences? Polluted water, ruined farmland, destroyed vegetation. Imagine your field site turning into a chemical soup. A major issue highlighted is the lack of regulation. While this in situ leaching technique was first developed in China, where it's now governed by quotas, standards, and environmental assessments to mitigate acid leakage, no such regulations seem to apply in places like Myanmar. This largely unregulated mining poses urgent threats to ecosystems and human health. Beyond the environmental catastrophe, this unregulated activity is also linked to conflict financing, providing significant income to armed groups. So, while commercial ISR might promise a clean future, we have to be extremely careful about how in situ methods are implemented and regulated globally. It's a bit like the difference between a careful surgical procedure and just hosing down the patient with chemicals. The name might sound similar, but the outcome is vastly different. Adding to the complexity is the global supply chain itself. Most reproduction is concentrated in a few countries, leading to vulnerabilities and risks of supply disruption. The supply chain is complex, often secretive, and tracing the origin and quality of REEs can be hard. This lack of transparency makes achieving sustainability goals within the industry challenging. Our demand for these elements in electric vehicles and wind turbines means that even well-known companies should be concerned about risks like environmental damage, social impacts, and conflict financing in their supply chains and undertake due diligence. Trying to trace a rare earth atom back to its geological birthplace through a complex global supply chain sounds like a detective novel I'd read. Given the environmental and social baggage of traditional mining and the ethical issues with unregulated in situ methods, there's a huge push for sustainable sourcing and diversifying supply. This is where earth scientists get to shine by looking beyond virgin ore deposits. One promising route is recovering REEs from secondary sources, basically industrial waste and recycled materials. Think of turning trash into treasure. Secondary sources include electronic waste like old smartphones check under your couch cushions, mine tailings, contaminated residuals from mine drainage treatment, red mud a byproduct of alumina refining, phosphogypsum from phosphate rock processing, and even coal fly ash. Coal fly ash, a major waste product from power plants, is abundant globally and its fine powder nature makes it amenable to chemical processing, although the REE concentrations are typically low. Life cycle assessment studies show that recovering REEs from secondary sources generally results in lower environmental impacts across many categories compared to primary sources. This includes lower global warming potential, reduced particulate matter formation, less toxicity, and decreased acidification and terrestrial eutrophication. However, it's not a magic bullet. Some impacts, like freshwater eutrophication, water consumption, and ionizing radiation, might still be higher depending on the specific secondary material and process. But overall, utilizing waste streams aligns better with a circular economy and sustainable resource management. It's definitely a more geoethically sound approach than leaving toxic legacies while digging new holes. Beyond waste streams, cutting-edge research is exploring entirely new ways to extract and separate REEs, often inspired by nature. One exciting development involves using recyclable protein biosorbents. Researchers have developed thermo-responsive, genetically encoded elastin-like polypeptides RELPs equipped with a lanmodulin protein, hence RELPs. Lanmodulin is a protein found in certain bacteria that are really good at binding to lanthanides. The RELPs act as a biosorbent, effectively recovering REEs from low-grade sources like coal fly ash leachate. The cool part is that they are recyclable using temperature cycling, retaining most of their binding capacity over multiple uses. This process relies on liquid-liquid phase separation or coacervation, where changing the temperature causes the protein and bound REEs to separate from the solution. They've shown they can selectively recover high-purity REEs even from very dilute solutions, achieving a massive increase in purity compared to the source material. This method requires less chemical input and energy, produces minimal waste, and has the potential for industrial scalability. It's pretty neat to think of using engineered proteins like tiny, selective sponges to sop up valuable metals. Another fascinating, nature-inspired approach is the development of artificial membrane channels. Inspired by biological membranes where transport proteins selectively move ions, researchers at the University of Texas at Austin have created tiny pores embedded in membranes that act like tiny gatekeepers, allowing only desired ions to pass. These artificial channels leverage the extremely subtle differences in how different REE ions interact with water when surrounded by water molecules, their hydration shells. Remember that tiny 0.02 nanometer difference in ionic RED. That slight variation in how the ion bonds with 8 or 9 water molecules is enough for the channel to tell them apart. This water-mediated interaction is the key to their selective transport. The goal is a cleaner, more precise way to separate and extract REEs, potentially applicable to other critical minerals too. It's biomimicry at its finest, learning from nature's elegant solutions. Beyond proteins and membranes, other innovations are emerging, such as electrokinetic mining (ECM), developed by researchers in China. This green and efficient technology is being developed for recovering REEs from ion adsorption deposits, offering another potentially more sustainable alternative to current problematic methods. Finally, underpinning all these discussions about extraction methods, supply chains, and recycling is the concept of geoethics. For us earth scientists and enthusiasts, geoethics means considering our responsibility not just to ourselves and colleagues, but importantly, to society and the earth system. For re-extraction, geoethics demands that we look at the social and environmental impacts. This involves responsible mining practices, minimizing pollution, managing land wisely, assessing health impacts, preventing climate change contribution, and protecting geodiversity. Extracting from secondary sources aligns better with geoethical principles by reducing environmental burdens compared to extract virgin ore. However, even with secondary sources, there's still work to be done to minimize certain impacts to be fully consistent with geoethics. It's about balancing the necessary exploitation of geo-resources by providing a healthy life and respecting ecosystems. It's a call to action for responsible solutions that integrate ethical and social considerations. So, next time you're wielding a rock hammer, think about the geoethical implications of what you might find. In conclusion, the world needs rare earth elements for our technological present and clean energy future. The traditional ways of getting them are often environmentally and socially costly. While promising technologies like commercial ISR are on the horizon, existing in situ methods highlight the critical need for stringent regulation and responsible implementation. Diversifying supply through recycling and utilizing secondary sources offers a more sustainable pathway, though not without its own challenges. Meanwhile, exciting new research is developing nature-inspired methods like protein biosorbents and artificial membrane channels that could revolutionize extraction with improved efficiency, selectivity, and lower environmental footprints. For us in the earth sciences, navigating this complex landscape requires innovation, strategic investment, and a deep commitment to geoethics, ensuring that meeting global demand doesn't poison the present while fueling the future. The rocks hold the keys, but how we unlock them matters more than ever.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 1,500 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights, but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 2,000 earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.